If you've ever read a headline claiming that hydrogen is inefficient, you're absolutely right. It is. But that's not the whole story. Hydrogen's inefficiency doesn't make it useless. It makes it strategic. And understanding that distinction is critical if you're a developer, consultant, or investor working in the green hydrogen industry. Today, we're unpacking the paradox: why the world still needs hydrogen, even though producing and transporting it is, quite frankly, energy intensive and expensive. This is the kind of thinking that separates surface level discussions from real project intelligence, the kind we cover in detail inside our green hydrogen project development and financing course at renewenergy.com. Let's start with a simple truth. When you produce hydrogen through electrolysis, you lose roughly 30 to 35% of the energy input right at the electrolyzer. Electricity from solar or wind has to split water molecules into hydrogen and oxygen. And that's a process with unavoidable thermodynamic losses. Then you need to compress, liquefy, or convert that hydrogen into something usable, like ammonia or methanol. Each step consumes even more energy. By the time the hydrogen is stored, transported, and reconverted into electricity, or used as fuel, you can lose more than half of the original energy. So, if you're comparing it purely to batteries, yes, hydrogen looks like the underdog. Battery systems can achieve 85 to 90% round-trip efficiency, while hydrogen systems often hover around 30 to 40%. On paper, that looks terrible. But in the real world, things are never that simple. Efficiency isn't everything. Imagine trying to use batteries for steel production, shipping, aviation, or chemical manufacturing. It doesn't work, not economically, not physically. Some industries don't just need electrons, they need molecules. Hydrogen isn't just an energy carrier, it's a building block for industrial chemistry. It's an essential ingredient for making ammonia, methanol, and synthetic fuels. It's also a potential replacement for fossil-based reducing agents in steelmaking. So even if it takes more energy to produce, hydrogen provides something electricity alone cannot: chemical flexibility. And that flexibility is where developers and financiers find real value. Let's take the example of green ammonia. To make ammonia, you need hydrogen. There's no way around that. Traditionally, it's been made from natural gas via steam methane reforming, a process that emits CO2. But if you produce hydrogen from water using renewable electricity and feed it into the Haber-Bosch process, you get carbon-free ammonia, a molecule with enormous potential, not just for fertilizers, but for shipping fuel, grid storage, and hydrogen transport. In places like Saudi Arabia's NEOM project, developers are investing billions into large-scale ammonia plants precisely because ammonia can serve as both a hydrogen carrier and a global export commodity. They're not doing this because hydrogen is efficient. They're doing it because ammonia is practical. It's easier to ship, store, and monetize. And investors understand that trade-off. The same logic applies to green steel. Conventional blast furnaces use coal or coke to remove oxygen from iron ore. That chemical reaction releases CO2. But hydrogen can do the same job. It strips the oxygen and produces water vapor instead of carbon dioxide. That's the core of what's known as direct reduced iron, DRI, steelmaking. Projects like Hybrid in Sweden are proving that green steel is not science fiction. It's already happening at commercial scale. Again, the process is not about chasing efficiency, it's about replacing carbon-intensive reactions with cleaner ones. And that's a game changer for heavy industry. Now, let's talk about transport, one of the biggest sectors where hydrogen could shine despite its inefficiency. Batteries are great for passenger cars and short-distance transport, but when you move into long-haul trucking, shipping, and aviation, weight and energy density become major constraints. Hydrogen has 3 times the energy per kilogram of diesel. That makes it ideal for heavy-duty vehicles that can't afford the weight penalty of massive battery packs. Refueling is fast, range is long, and downtime is minimal. Companies like Toyota, Hyundai, and Nikola are already deploying fuel cell trucks in pilot corridors. Meanwhile, maritime players are exploring ammonia and methanol as hydrogen-based fuels for ships, because they're easier to store than pure hydrogen. Even aviation is entering the picture. with Airbus exploring hydrogen-powered aircraft by the 2030s. Again, efficiency isn't the key metric here, it's feasibility. These industries need energy-dense, portable, and clean fuels. Hydrogen delivers that, even if it costs some efficiency along the way. But perhaps hydrogen's most underappreciated role lies in energy storage. As we move toward 100% renewable grids, we face a new challenge: intermittency. Solar and wind are variable. Batteries can balance the grid for hours, but not for weeks or months. Hydrogen, however, can be stored in large volumes, even underground in salt caverns, and reconverted into electricity when needed. It acts as a form of seasonal energy storage, something no other clean technology currently does at scale. In Germany, projects like Hystock are already injecting green hydrogen into salt caverns to store renewable power from wind-rich seasons for later use. The round-trip efficiency may be low, but the system-level value is high because it provides flexibility, resilience, and reliability. For grid planners and financiers, that's a compelling proposition. If you zoom out and look at the entire hydrogen value chain, you'll see why developers still pursue these projects despite the inefficiencies. It's not about direct efficiency, it's about system optimization. Hydrogen adds diversity and resilience to the energy ecosystem. In markets with abundant renewables, think Australia, Chile, Namibia, and parts of the Middle East, hydrogen acts as a bridge between excess generation and global demand. It converts local renewable power into a tradable molecule, enabling countries to export energy just like oil and gas once did. That's why nations are building hydrogen export terminals and infrastructure. It's about turning electrons into molecules that can move across oceans and create economic value far beyond the grid. For developers and investors, this shift means opportunity, but it also means understanding the economics behind the inefficiency. When you look at levelized cost of hydrogen, or LCOH, inefficiency translates into higher production costs. Every kilowatt hour lost in electrolysis or compression adds to your cost per kilogram. That's why the race is on to drive electrolyzer efficiency higher and electricity costs lower. Today, green hydrogen production typically ranges between $4 to $6 per kilogram, depending on region and technology. The holy grail is $2 per kilogram, the point where green hydrogen becomes competitive with fossil-based hydrogen. To get there, developers need to focus on several levers: low-cost renewable power, high electrolyzer utilization, optimized water supply, and smart financing structures. And that's precisely the kind of techno-economic modeling we teach inside our green hydrogen project development and financing course. Let's be honest, hydrogen is not going to replace electricity for everything. You'll never power your smartphone or your home toaster with hydrogen. But if you're working in decarbonization, you quickly learn that there's no silver bullet, only sector-specific solutions. Hydrogen fills the gaps where direct electrification struggles. It decarbonizes industry, balances grids, powers heavy transport, and provides chemical feedstock for essential products. And it creates a whole new landscape of investment opportunities for those who understand its nuances. Consider the infrastructure angle. Producing hydrogen is just one piece of the puzzle. You also need pipelines, compressors, liquefaction plants, storage facilities, and refueling stations. Each of these components adds capital costs but also creates opportunities for project developers, EPC contractors, and technology providers. Investors are already positioning themselves around these assets, betting that as hydrogen demand grows, so will the need for midstream infrastructure. For example, in Europe, the Hydrogen Backbone Initiative aims to convert existing natural gas pipelines into a transcontinental hydrogen network. That kind of infrastructure build-out could rival the early days of the oil and gas industry. The inefficiency is baked in, but so is the value. And then there's hydrogen's role in global energy security. In a world increasingly aware of geopolitical risk and supply chain fragility, hydrogen offers diversification. It allows countries to produce their own clean energy from domestic renewables instead of relying on imported fossil fuels. It can turn energy-importing nations into energy exporters. Think about Morocco's plans to supply green ammonia to Europe or Chile's ambitions to become a hydrogen superpower by leveraging its Atacama Desert solar resources. These projects are not just about technology. They're about economics, sovereignty, and positioning in the next global energy market. For all these reasons, the hydrogen industry is projected to attract over $110 billion in committed capital by 2025, with more than 500 projects under development worldwide. Yet the majority of them still face financing hurdles, regulatory uncertainty, and cost pressures. That's why understanding the business side of hydrogen is just as important as understanding the chemistry. Developers who can build solid techno-economic feasibility studies, secure offtake agreements, and structure bankable finance deals will be the ones who succeed. In a market where inefficiency is a given, value creation depends on strategic positioning. Knowing where hydrogen makes sense, how to de-risk projects, and which financial models actually close deals. One of the most common mistakes new entrants make is focusing too much on efficiency metrics and not enough on project viability. Investors don't fund efficiency, they fund profitability and scalability. That means your hydrogen project has to make economic sense in its specific context. For example, a project near a port with industrial off-takers and cheap renewable power can thrive even at lower efficiency. But a project in a remote area with limited grid access and expensive logistics might fail even with a high-efficiency electrolyzer. Understanding this balance between technical performance and economic feasibility is what turns a concept into a bankable project. And that's what our course equips you to do. As the hydrogen sector matures, expect to see more hybrid models emerge. Projects that integrate hydrogen with batteries, carbon capture, or direct air capture to optimize system efficiency. Developers are learning that you don't have to pick one technology over another. The future energy system will be a mosaic, with hydrogen serving as the connective tissue between renewables, storage, and industry. Efficiency will always matter, but it won't define success. Strategic integration will. Now, there's another layer to this discussion: public perception. The hydrogen inefficiency narrative is often used by critics to dismiss the entire industry. But what they overlook is that efficiency is only one dimension of performance. Water electrolysis might lose 30% of the input energy, but if that electricity would have otherwise been curtailed due to grid congestion or overgeneration, then using it for hydrogen production adds value. It converts stranded renewable energy into storable chemical energy. It prevents wasted capacity. In markets like California or Germany, where solar curtailment is common, hydrogen becomes not just a fuel but a grid management tool. In the coming decade, efficiency will improve anyway. Electrolyzer technologies are evolving rapidly, from alkaline to PEM to solid oxide designs that can recover heat and integrate with industrial processes. Innovations in catalysts, membranes, and system design are pushing conversion efficiencies toward 80%. And once those gains combine with cheaper renewables and optimized project financing, hydrogen's inefficiency will become less of a liability and more of an engineering challenge that developers know how to manage. So the next time someone says hydrogen is inefficient, the correct response isn't to deny it, it's to explain it. Yes, hydrogen is inefficient in isolation, but in the context of a global multi-sector energy system, it's indispensable. It fills the gaps where electrification can't reach. It provides storage where batteries can't last. It delivers molecules where industries can't use electrons. And it creates economic pathways that tie renewable generation to real-world industrial demand. That's not inefficiency, that's strategic design. For developers and consultants, this understanding can reshape how you approach project feasibility. When you prepare your techno-economic analysis, factor in not just efficiency, but use case fit. When you model your LCOH, include flexibility and offtake security as value streams. And when you pitch to financiers, frame hydrogen as part of an integrated decarbonization strategy, not a standalone technology chasing efficiency. That's how you make your project bankable. That's how you bridge the gap between engineering and investment. Hydrogen's inefficiency forces us to think bigger. It's not about perfect systems. It's about possible systems that move us closer to net zero. Every kilowatt hour that goes into hydrogen today is part of building the infrastructure, knowledge base, and supply chain of tomorrow's energy economy. It's a long-term play, one that rewards vision and patience, qualities that define successful developers in emerging industries. So, yes, hydrogen is inefficient, but it's also essential. And for those who understand both its limitations and its potential, it's one of the most exciting frontiers of clean energy innovation. If you're a developer, consultant, or investor looking to navigate this complexity, from feasibility studies to financing structures, our green hydrogen project development and financing course at h2hub.renewable.com is designed for you. It's a 10-module program that breaks down the full project lifecycle from concept to commissioning, with real-world templates, financial models, and case studies. You'll learn how to evaluate LCOH, structure offtake agreements, engage financiers, and make your hydrogen project truly bankable. Visit h2hub.renewable.com or explore our tools on h2hub.renewable.com to start building your expertise in this new hydrogen economy. Because while hydrogen may be inefficient, the opportunities it creates are anything but.